So you've already learned about both the law of sines and the law of cosines, and you've used them to find the missing angle in a triangle, the missing side in a triangle. So what we're going to do here is see how these can be applied to, more practical applications that we might encounter in real life. So one of the ways that a lot of times information is going to be presented to us when we're talking about angles is as either a heading or a bearing, right? So anytime we're talking about an object that's moving, we might be saying, okay, it's as a heading of this or a bearing of this. All right. So while I'm not going to use this notation a lot, I want to at least explain what it's about. So if you see something like this, that means a bearing of 30 degrees east of due north. So this N here means that you start by pointing yourself due north and then you move 30 degrees east of that. So that shorthand notation literally means 30 degrees east of the due north line. And so what that means is when you're just kind of sketch a due north line and then you say, okay, there's 30 degrees, and so that's where I'm headed. All right, so let's take a look at example one here and see if maybe the law of sines, the law of cosines could be appropriately used to give us an answer. So it says a ship leaves port at 1 p.m. and travels 35 degrees east of south at the rate of 24 miles per hour. Another ship leaves the same port at 1:30 p.m. and travels 20 degrees west of south at 18 miles per hour. Approximately how far apart are the ships at 3 p.m.? So we've got these two ships. Now, they're both talking about going east or west of south. So what we should do is begin by just having a line that runs north to south. And so we have the first ship. It went 35 degrees east of south. So that'll be something like this. Right, so we'll say that's 35 degrees east of south. And it's going to go for a while, right? From 1 p.m. to 3 p.m. And it's going at 24 miles per hour. All right, now, so we'll label this as 35 degrees. Now on the other side, our other ship, use a different color here, only went 20 degrees west of south, so we have a different angle here. And it didn't travel for as long, and it also traveled slower. So we're definitely going to expect this one to be quite a bit shorter than this one, but we'll put 20 degrees in right here. All right. And so it says approximately how far apart are the ships at 3 p.m. So at 3 p.m., we should be able to say what this distance right here is. Okay, so the question then is, okay, can we make sense out of these sides here? Because I can clearly see that I could combine these two angles that I have and state that this is 55 degrees just by putting them together. So do I know anything else, right? I don't know this angle, I don't know that angle, but I should be able to figure out these side lengths. So let's start with the first ship, right? What do we know? It went for 2 hours and it went at 24 miles per hour. Well, if that's the case, we can figure out exactly what that length is, right? That should be 48 miles, right? And it's just 48 miles because we're taking 24 miles per hour times 2 hours. And then our red one, we should be able to figure out as well. It went for an hour and a half, 1.5 hours, and it went at 18 miles per hour. So that one I can say is 24 miles. Why? It's 24 miles because it's 1.5 hours times 18 miles per hour. Now, let's think about what we learned in the previous topic when we're talking about law of cosines, law of sines. When do we want to use each one? Well, remember that if you know two sides and the angle between them, then you can easily find that third side with the law of cosines. So I can just simply say that d squared has to be equal to 24 squared plus 48 squared minus 2 times 24 times 48 times the cosine of 55 degrees. Okay, so just remember everything on the right side here, its relationship, it's the two sides appearing and then the angle between them appearing. And that gives you the square of that opposite side of the angle. And of course, I'll take the square root of both sides. And if I, kind of combine this, this is going to be 2880 minus 2304 cosine 55 degrees. So when I do that computation, I get about 39.5 miles. And let's make sure that that makes some sense here. If I've got 24 miles here, 48 miles here, yeah, it seems reasonable that they'd be about 39.5 miles apart, according to my picture. Now, what you will see me do a lot is when I'm using law of cosines, a lot of times I'll probably just say from the outset, d equals the square root of all this. Okay, so don't be thrown off if we do that, just to cut down on the number of steps we got to take in our writing. All right, let's look at one other example. It says that we have two towers located 7 miles apart on a mountain ridge. Tower A is directly north of Tower B, and a fire is spotted bearing 70 degrees east of south from Tower A and 85 degrees east of north from Tower B. How far is the fire from Tower B? So you can see why this would be important, right? If you have two different observation towers and you can just figure out the bearing and you know that the distance between the towers, you can actually figure out how far away that fire actually is. All right, so let's first just sketch the two towers, right? We have Tower A up top. We have Tower B down here, right? Running north-south. They told us this is 7 miles here, right? But then we have these so from Tower B especially, 85 degrees east to north, that's really close to a 90-degree angle. So I've got to go all the way almost to 90 and go out in that direction to find that fire. And then A, I don't have to go, it's not quite as steep, but still pretty steep. It's 70 degrees east of south. So that's going to be something like that. And let's see, that probably not even that accurate. Like, the 70 degrees here, that kind of doesn't, that looks a little, yeah, that's definitely not 70 degrees. So this is a video and it's being preserved for all time, let me do a little bit better job here. So 70 degrees, maybe something more like this. Okay. All right. So here's our fire. So what did they ask? How far is the fire from Tower B? So that means we want to know this right here. All right. Now let's think about what we know. We want to know x. In the last problem, we were able to find our distance, or the side of one of our triangles, because we knew both sides that are on either side of this opposite angle, but we don't know this side here, right? So that means law of sines or law of cosines might not be the right choice. So let's think about the law of sines. So the law of sines says if I take the sine of 70 degrees over the side opposite of it, that could equal the sine of, well, if I want to involve the side I know, I want to put 7 down here. But then I up here have to put the sine of whatever this angle is. But luckily, since I know two other angles, I do know what that angle has to be. That has to be 25 degrees. It has to be 25 degrees because it's got to be whatever's left after you take away 70 degrees and 85 degrees from 180. So we'll put 25 degrees there. And of course we can multiply on both sides to get x out of the denominator. Give myself some more space here. And then of course we can divide by the sine of 25 degrees. So my x is equal to this, which is well, I guess I'll just write it out, sine of 70 degrees over sine of 25 degrees, and then punch that in the calculator to get an approximation of about 15.6 miles. All right, and let's see if that makes some sense. All right, well, you know what? I'm looking at this. This is supposed to be 15.6 miles. And you know what it tells me? It tells me that this is supposed to be twice as big as this, right? Approximately 15.6. So that means my picture's not great, okay? So in reality, I'm looking at this 85 degrees, and that looks like maybe it's a little less than 85. This is probably a little less than 70, which makes the fire appear closer here. So I don't think I did anything wrong. What I'm thinking is, if I really want to represent 70, probably needed to be a little more like this. And if I really wanted to represent 85, it needed to be a little bit more like this. And so in reality, here's probably where the fire is. And so then that, looks a little closer to twice as big as that. So this is one of those things where you always check your work, always make sure that your picture at least somewhat agrees with the answer you're getting. At the same time, understand that when you're approximating how big an angle is, you are susceptible to error there, as am I. And so we don't want to just throw it out the moment it doesn't perfectly match our picture. We want to think, okay, is maybe my picture slightly inaccurate, or did I make some sort of algebra mistake?